Okay, welcome to this session which is titled Assessing the Maximal Oxygen Uptake, VO2max. So the aim of this session really is, as you can see, it's threefold. Firstly, we're going to establish a framework for the assessment of VO2max. That is, why do we assess this? And in many ways, this is the heart of pretty much everything that we do within the field of exercise sciences, but science generally. We have to have a rationale for why we are going to do what we're going to do. And in many ways for VO2max, there's a very strong rationale for this, particularly within the clinical population groups. We're then going to address the how we assess this. So this is the idea of protocol design and the ramifications of protocol design in terms of the outcome of the test. So we're thinking here in terms of the validity of the test or the design of the test that we use, and also the reliability of this. Now this really takes into account, for example, the choice of ergometer that we may use, the nature of increase in exercise intensity or resistance that we're going to use, and then also fundamentally the way in which we're going to collect the fundamental marker, which is the expired air, for the recording and monitoring of the O2 and CO2 concentration, and therefore the VO2 and VCO2 scores. And then perhaps the most contentious part of this, which is the notion of a volitional exhaustion and a true maximal effort, because the whole premise of VO2max is by definition that the participant or the patient has gone to the point of volitional exhaustion. That is, we're at the point where both the cardiac output and the AVO2 difference are maximal. And we have to then be certain that they have given us a maximal effort to define it as a VO2 max. So how do we define this as a maximal effort and not somebody who has stopped because they are fatigued? And we have to understand that distinction between what is perhaps fatigue and what is exhaustion. Now, in order to kind of better understand VO2max, it's worth perhaps looking back in the literature for it. And this is from a seminal paper published in the mid-90s by Bassett and Howley. So Howley is the lead author on this one, which they write quite clearly, as you can see. Maximal oxygen uptake is defined as the highest rate at which oxygen can be taken up and utilised by the body during severe exercise. It is one of the main variables in the field of exercise physiology, is frequently used to indicate the cardiorespiratory fitness of individuals. In the scientific literature, an increase in VO2max is the most common method for demonstrating a training effect. So it seems to have a significant place within the field of exercise physiology. The definition that they've given us is very important. It's the highest rate, and I want to come back to that term rate. It is a rate-based measurement. It is not a measurement of capacity, and this is one of the areas where there is a lot of miscommunication within the field of science, in that it is quite often defined as a measure of aerobic capacity. Excuse me, yet the variables, the units for the variables are in either litres or millilitres per kilogram per minute. It becomes rate-based. The second point that they make is that it's utilised by the body during severe exercise. Now, if you're following a course of these video casts, or you're just learning perhaps more about exercise physiology, make a note of that, because that severe exercise part really connects with our understanding in a subsequent presentation into the role of what we call oxygen uptake kinetics and exercise domains. They've given us clear license for why this is undertaken. Clearly, they're talking about here it's got a place in fitness, and that could be fitness in terms both of clinical and maybe in athletic population groups. But it's also used to demonstrate things like training effects. It's used in studies where we're monitoring perhaps even nutritional responses and ergogenic aids. It is probably one of the most widely reported variables in the field of exercise science, but almost certainly within the field of exercise physiology. So we have a strong context, a strong rationale for why we may want to assess this as a parameter. Now, in order to perhaps understand what we do now, we need to go back. And we need to go back into the 1920s and a series of seminal papers published in Cambridge in the UK, published by A.V. Hill. This is Archibald Vivian Hill. This is who you can see here on the screen. And in fact, what you can see here is one of a series of papers that were presented and published in the journal, which is Physiology, back in the 20s, over about a 3-year period from about 1922 to 1925. And he did a lot of this work with his colleague Lupton, who's also on this paper. Why is this so important? Well, it's so important because Hill was really the first individual to run a VO2max test. Now, that's not to say that previous authors leading up to this work in the 20s weren't speculating about a limitation in terms of exercise tolerance, but he was the first really to do this, and he did this by running a series of repeat trials on himself, and he did 42 repeat VO2max tests, and in many ways they perhaps look similar to what we would do now. He was doing them outdoors on a running track, and they were using open circuit spirometry, that is collecting into pre-evacuated Douglas bags, and he would run at faster speeds with a little break in between each one, and it would be his colleague Lupton who would be collecting the air into the bag, who was alongside him on a bicycle. And so Hill really was the first to postulate the kind of the dynamics of the VO2max. In fact, he goes on to write some very, very important comments within his paper about the factors which govern the VO2max. And it's really from that understanding that in the 1920s that all of our current thinking stems. And in fact, what was staggering in many ways about the work of Hill was that Hill was really referring to things like cardiac output, which we'll talk about in a moment. He was referring to muscle energetics, when actually, you know, there were very, very few techniques available for recording those. We certainly hadn't identified ATP at that point. So he was really kind of at the forefront of this and was very much a pioneer within the field of exercise physiology. Now, coming forward, this is a fairly recent paper published by Carsten Lundby, and the paper is a tremendous review in terms of kind of the dynamics of VO2max. But what is so important about this is as a paper, it sets out for us the kind of the physiological definition of VO2max. Now, the Howley and Bassett paper gives you perhaps more of a word-orientated definition, but this is really what VO2max is if we're thinking about it physiologically. To hit the VO2max, that's the maximum volume of oxygen which we can use, that we can take up and use. So it's basically the amount of oxygen you can take up from atmospheric air and use for the aerobic generation of ATP. So that is actually a function of this equation here. Now, if you've studied earlier sessions within this course, or you've got some understanding of exercise physiology, you'll recognise this. This is the Fick equation. So the Fick equation simply states that VO2, in this case VO2max, equals SV, which is stroke volume times heart rate, times AVO2 difference. So the key thing here is that for us to be at the VO2max, we have to be at maximal stroke volume and maximal heart rate. In other words, we have to be at maximal cardiac output. There cannot be any more blood being ejected per beat of the heart, that is our stroke volume, and we cannot have the heart beating any faster. If we could, then fundamentally we would be in a position to deliver more oxygen to the tissue. At the tissue, we also have to be at max to be at VO2 max. That is, we have to be at maximum AVO2 diff, that is the maximum amount of oxygen being extracted per beat of the heart. So the Fick equation really informs for us what is happening at VO2 max. And what is quite nice is in this schematic you can see all the factors that fundamentally drive these physiological responses. So you can see, for example, that the AVO2 difference is a function of things like red blood cell volume, and what he's referring to here is how long these would respond to training. So most of the kind of the physiological responses that we see are quite chronic adaptations. They're quite long term. The only acute response is the change in the plasma volume that we get. And the change in the plasma volume affects the AVO2 difference because it changes fundamentally the viscosity of the blood. But all of these factors fundamentally dictate the change in the VO2 max. And typical VO2 max for the general population, for perhaps somebody who's relatively sedentary, fit but relatively sedentary, is in the region of about 42 to 45 mils per kilogram per minute. We start to get into the realms of endurance capability. We're thinking about endurance athletes. We're looking at the region of 65 mils per kilogram per minute plus, and really starting to get into the really stratospheric VO2 max scores when we're getting into the regions of 75 mils per kilogram per minute plus. So in Tour de France cyclists, we're looking at VO2 maxes into the 80s. Cross-country skiers, we may well be looking at VO2 maxes into the 90s. Whereas actually, if we come down, for example, to marathon running, actually we tend to have slightly lower VO2 maxes, late 60s, early 70s. But that's perhaps because that kind of event is perhaps more associated with something like economy.